Welcome to Automating Serverless Deployments for DevOps Organizations. I am Daniel Sokolowski, and this is joint work with Pascal Weisenburger and Guido Salvaneschi that we started at the Technical University of Darmstadt in Germany and continue at the University of St. Gallen in Switzerland. The way software is developed and operated is changing continuously. Today, companies want to improve their software delivery and operational, short SDO performance, which indicates the throughput and the stability of their organization. Thereby, they notice that changing how software is developed is not enough. Also, software operations must be taken into account. Between these two silos, usually there was a wall that causes friction, diminishing the SDO performance. To improve, DevOps organizations aim to tear down this wall and bring development and operations close together in cross-functional DevOps teams. Ideally, each team develops and operates their software independently from other DevOps teams. But is that even possible? Let's look at this T-Store webshop, which is built following microservices architecture. Under the hood, it consists of separate microservices. However, they depend on each other. Each arrow in this picture is such a dependency. If for each service a separate DevOps team would be in charge and these teams shall be independent, can we just ignore these dependencies and everything will work out? We tried it and, well, clearly here the answer is no. But that made us wonder, are DevOps teams really that independent? Are there indeed software dependencies that require them to ensure a correct order of deployments? Is all that really a problem? To find that out, we performed a survey under 73 IT professionals in industry. We first asked them, how many other applications must be deployed so that the primary application you work on provides all its functions? We found that most applications require such a dependency, most of them 2 to 5, for a third even more. We then asked whether they agree that such dependencies constrain the order of the deployment and the undeployment operations. And most of the respondents answered that this can be the case. We further wanted to know whether they coordinate these deployments manually by using chats, phone or emails, or whether they use an automated solution. Most of the respondents rely on manual coordination approaches. We also tested through a set of different questions how much they agree that automated coordination of the deployment order yields better SDO performance than coordinating manually via phone, chat or email. In this construct, 0 is neutral and positive values express agreement that automated deployment coordination yields better SDO performance. And most participants clearly agreed. Let me introduce an example now. A simple static website. It is unrealistically simple, but enough to show the ideas. The website is an AWS S3 bucket and an index page, which is deployed inside the bucket. A common representation format of such deployments are resource graphs, where each resource is a node and the arcs are dependencies between them. Here, the index depends on the bucket. The arcs constrain the order of the deployment and undeployment. In this example, the bucket must be deployed before the index, and before the bucket can be undeployed again, the index must be undeployed. Each resource is maintained and operated by a dedicated team, the bucket by the provider and the index by the editor. Considering this example, the first use case for deployment coordination is asynchronous deployment. When the editor starts their deployment first, the index should only be deployed after the provider deployed the bucket. Vice versa, safe undeployment requires deployment coordination. When the provider undeploys the bucket, the index must be undeployed first. Lastly, consider the index shows the bucket's name. Then, whenever the provider changes the bucket name, deployment coordination is needed to forward this change and to update the index page. Today, deployment coordination is either manual or it is automated in a centralized fashion. Manual coordination means that in any of the 3 use case scenarios, the provider and the editor have to phone, chat or mail each other to ensure correct interaction. Centralization means that all operations are performed by a central team or central system which ensures the correct order. While only manual coordination requires frequent synchronization among teams, both contradict independence of the teams. This threatens the flexibility, throughput and stability of the organization. There's clearly need for a system that automates coordination in a decentralized fashion. We close this gap by introducing Muse, a novel infrastructure as code solution. Muse features decentralized automation of the deployment coordination by ensuring that each team has a separate deployment that they can start and stop independently. In these deployments, the teams can explicitly offer resources to each other and wish for them respectively. The deployments run as long-running processes instead of one-off tasks, and their runtimes exchange updates of offers reactively. Let me show you the details with our website example. This deployment can be described by these 6 lines of TypeScript in Pulumi, which is an industrial-strength infrastructure as code solution Muse builds upon. We split the code into separate deployments for each team. Then we make the connection between the deployments explicit by referencing the other deployment with a remote connection resource. The provider then defines an offer resource which offers the bucket to the editor. The editor defines a wish resource for the bucket offer which completes our 2 Muse deployment descriptions. Let's have a look how these Muse deployments behave in the 3 use case scenarios of concern that I mentioned earlier in the talk. First, asynchronous deployment. The index shall be automatically deployed once the bucket is available. Let's step through it. The editor starts the deployment. Then the remote connection to the provider and the wish for the bucket are deployed. But the wish is unsatisfied, therefore the index is not deployed yet. Then the provider starts the deployment and the remote connection to the editor and the bucket are deployed in parallel, followed by the offer. The deployment runtime directly forwards the offer to the editor's deployment, which then automatically deploys the index because the wish is now satisfied. The website is fully deployed now. Let's consider that the provider changes the bucket name, which is displayed on the index page. On the update of the bucket in the provider's deployment, the runtimes transport the change and update the index automatically. The last use case is safe undeployment. Let's consider that the provider stops their deployment first. Muse withdraws the offer, which is sent to the editor deployment that then automatically undeploys the index because the wish is now unsatisfied. The editor deployment signals that no resource depending on the wish is deployed anymore, which completes the undeployment of the offer in the provider's deployment. The remote connection to the editor and the bucket are then undeployed in parallel. This brings us to the evaluation. We implemented the deployments of the T-Store in Muse, Pulumi and AWS CDK. Muse is the only solution where this coordination is automated. This comes at the small cost that Muse requires a bit more coding than its competitors, because the interfaces between the deployments are explicit in the code. However, both insights confirm that Muse supports DevOps organizations effectively. To evaluate Muse performance, we considered the deployment of a simple web service. Muse showed to deploy that service roughly as quick as Pulumi and faster than AWS CDK. We then deployed multiple instances of this web service with parallel and sequential dependencies between them. The graphs show for the multiple repetitions the number of deployed resources during deployment and undeployment. As expected, Muse deployment coordination does not introduce a significant delay to the deployments. In summary, Muse does not perform worse than its competitors. Lastly, we studied Muse applicability. For this, we created a dataset of 64 open source Pulumi TypeScript projects on GitHub that use stack references. We migrated all these projects to leverage Muse deployment coordination by defining offers for the supplied resources and replacing stack references with wishes. This migration was fully automated using abstract syntax tree transformations and successful in all cases. This shows that Muse is applicable to real-world projects. This was automating serverless deployments for DevOps organizations. We wondered whether DevOps teams are really independent or whether they need to coordinate because of dependencies between their applications. Through a survey, we found out that this is indeed the case. We then looked at the use cases that require deployment coordination and proposed Muse as first solution that automates the deployment coordination in a decentralized fashion. We demonstrated Muse in detail and evaluated that it is effective, performant, and applicable to real-world projects. We are now at the end of this talk. Find out more in our paper. All our data and software is released publicly for you. Check it out and reuse it. Also, visit us on muse.rocks, GitHub, and follow us on Twitter. Thank you for watching. I'll be happy to take your questions and comments now in the live Q&A session or via any other way you get in touch with us.